measure. So this was a very important result of the 17th century. Then we had to wait until the beginning of the 19th century to find out that light was a wave. In the early 1800s, interference of lights were observed. An interference experiment consists in taking a light beam, separating it into two parts, and then recombining the two parts. One way to do it is to use a double slit, like shown here. This is a Young experiment. Or Fresnel did it in a slightly different way, using a double prism, but the idea is the same. And when you look at the light, when the two beams merge after having been separated, you find dark and bright fringes. There are some points where light is stronger and some points where it is weaker. And the only way to explain it is to assume that you have two waves which interfere. At some places, the waves add their effects, and at other places, one wave is up, the other is down, and they cancel each other. This is dark fringe. And there is no way to explain that by the particle theory, classical particle theory. So it seems that Huygens won over Newton at that time, and one knew that light was a wave from the beginning of the 19th century. Then another big development of the 19th century was the precise measurement of the velocity of light, not in space, not in the solar system, but on Earth and in the lab. And also the measurement was done either in vacuum or in air and in water to compare the velocities in a transparent medium and in water. The first guy who did that was Fizeau in 1849. And in fact, he resumed Galileo experiment, but with modern technology. So instead of having an assistant here, he put a mirror. Of course, the mirror reflects immediately. You don't have a tenth of a second to realize that there is light, as the mirrors are reflecting without reflecting. In French, we say réfléchir sans réfléchir. So it's impossible to translate in English, but it reflects immediately. So the light was shocked by this wheel, which has teeth here. And so you have a pulse of light going here, coming back, and the teeth is rotating very fast. So if one hole of the wheel is replaced by the next hole, the light will go through. And by knowing how many teeth you have on the wheel, how fast it goes, and what is the distance, here it was about 8 kilometers. He did the experiment between Paris and the suburb. They were able to deduce a value for the velocity of light. And about 12 years later, Charles Foucault made another measurement more precise. What he did is replace this mirror by a rotating mirror, very fast. And the idea is that the pulses of light coming on the rotating mirror will be deflected in a different direction, and then you measure the velocity of light by looking at the angle that the reflected light makes. And this angle depends upon the time it takes for the light to go from the wheel to the mirror. And by doing this more precise experiment, he was able to reduce the setup to the size of a lab, a few meters, and to get more precision. And they both found that the velocity of light is very close to 300,000 kilometers per second. And moreover, by putting a cylinder full of water, Foucault was able to find out that light is slower in a material medium, which is in favor of the wave theory, because the wavelength decreases in the medium, whereas according to Newton theory, and I don't have time to discuss, the result was that light should go faster in water, which was not the case. So this was a confirmation of wave theory. But the big question which remained is, okay, light is a wave, but a wave of what? What is oscillating? What is vibrating? And again, the answer came in a way which was not expected from discoveries which were made in fields which seemed to be completely disconnected with optics.